There you go. Yeah. No audio for this. And we're with, I think, 3 participants. Matt, okay, Matt, very good. Okay. Oh, good, yeah. No. Yeah. I just got. What? How was your weekend? Good. All right, normal.
What did I do? I finished my homework, the class. Oh yeah, I finished some project which I managed, which is good. How was your weekend?
Our weekend was busy.
Busy,
Yeah,
a
busy.
lot of interviews for the class.
No, no, I almost happy for the class, but I did post some stuff. Um. So you're first as always.
I'm first.
Yeah, I remember how we say it when somebody comes 100% increase in attendance. Let's
Yeah.
see, let's see if anybody else comes today.
Yeah,
We
let's
have
see.
2 people online.
I'm not a morning person. I'm surprised myself that I'm in time always. I set my alarm clock a quarter hour earlier, maybe that was good. Otherwise, I was always tight. Yeah.
So did you have to change your password? Because I think,
I
they told me a week ago that you had something cached that wasn't the same as the thing that you were typing.
Yeah, I had, because we have several accounts, right? We have the IU account and we have the
You have to change.
Microsoft, as a, something is our IU all the same, and then the Google is somehow all, or I don't know, there was at least two passwords and one of them had one letter less, and that was.
And then you showed me that one, which I didn't see very well, but still,
Yeah, that was the one that I,
did you refresh that?
now I have to put on new password and it's changed everywhere here. Yeah.
So it's almost 8:45, we have two people online, and I might as well get started. I'm recording since maybe 5 minutes ago. So. 210, welcome to week number 2. I'm going to go and say chat, and you can't see me, but if I were to enable the video, you could see me, I suppose. And I'm gonna cut the video again, and that's because I noticed on the recording from the iPad on Friday that some video was duplicated, that little thing was duplicated twice. Duplicated in the wrong place, it showed up once, and then again, and it shouldn't have shown more than once. So there's one more person in line, online, one more person in the room. And that's very good. Let me write them down. I think people are joining, and so we can get started. So maybe today I'm gonna take a picture of you, if you don't mind.
Oh, for the GitHub?
Or if you know, not for the GitHub. For the, you're right, for the page with the GitHub.
Yeah.
I couldn't find anything about you on my own account that I don't know you found it in. Cause it's just a PDP.
Oh,
period.
okay, yeah.
So. But that's all right, as long as you give me a picture,
Yeah, sure.
there's no problem.
Yeah.
Okay, so we're ready to get started. I have a chat. In the chat. So just to make sure people can hear me, would you please write your last name backwards? If you can hear me. So we had Ahmad. Then hopefully the others, they're very good. And then we have Sanmi now that has to write the name backwards. And since we only have 3 people online, that's right now 66% of people wrote their name backwards. I want to write mine too, to encourage Sanmi to write it, so I'm going to type like this. There you go, that's me. So as of right now, we could easily say behind us 1 week. What did we do in that first week? We mainly introduced the environment in which we are. That's perfect. Thank you. So everybody can hear me, and if you need to ask a question or stop me, you can write in the chat or you can just speak up. Right now, we haven't checked that people online can talk in such a way that we can hear, but I'm going to check with Sami, who is the most recent person to write his name in the chat. And I'm going to ask him a question. So the local time in Bloomington here seems to be 8:47. I'm gonna close this one. I'm gonna go to the website. And I'm gonna say, besides the fact that I started talking about what we did last week, and there must be a topic for the theme for the week. Then there's another one for this week and so on. I'm gonna go to C290. And I'm going to say that on Monday, when a week starts and another one sort of had finished 3 days ago, we should try to connect to the previous weeks and get started with a new material. So if I click here and I go on the 19, which is a special week last week for lots of reasons, these are the actual meetings that we've had already. I've had 6 meetings. And I see that for Sanmeet, I don't have anything scheduled. So I would like Sanmeet to talk to me right now, if he can talk. This is a test of audio. I mean, if he's in a place where he cannot talk, say so in the chat. But Sanmeet, when do you think you might have the meeting?
I'll be scheduling one by tomorrow, like for tomorrow, if something is available.
Sure, that's fine. If you say that tomorrow, then essentially, that's great. All the meetings that we set are basically through email. I know that I try to keep track of them in the office hours. And one person, I'm gonna close the chat. We heard Sanmeet and everything is good. We have Jack as well. So online we have Jack. And with this, I'm gonna close my taking attendance and I'm gonna start whatever we do here. And I'm also going to close these flow team controls that you guys cannot see unless I were to show you the screen or unless you're in this room. And I say, listen, I really am trying to keep track of these just for my own sanity and so on. But the scheduling for these meetings shouldn't be done through this script, should be done with me by email. And that's why I wrote this thing here, this table, so that we can keep track. So please don't forget, Sanmeet, if you decide that Tuesday is good for me, then look at the times and then email me and say, I'd like this time on Tuesday. Today I'm going to meet at 12:30 of those people who are present. Let's see, Ashish is coming tomorrow. I see Elmar at 11:30. I think Ahmad is also coming at noon. Then, as I said, Mr. Clevenger over here at 12:30, and then we have Sanmeet perhaps in the future. And then we have Jack. Jack is at 11 o'clock. So all the meetings are going to be through Zoom. And then if you say, I don't know what Zoom to use, it's the Zoom that you're using right now, or it's the Zoom that appears on this page. Great. And so the emphasis last week was on establishing the environment in which we do all the work. And I'm going to say that I wrote a notebook, which I find right now, but now I can't. The notebook contained 3 things, but each thing basically had more than one component. The first problem had 2 aspects. Here's some code, here's some text, which is in LaTeX, that sort of explains what the math is. Here's some program, here's another program. The program we wrote the day before is not in this notebook, but it will be that one. And then it's the circuit that we put together, whereby at the end, we can ask Qiskit to give us the outcome. And we said that we have established a procedure last week to keep track of what's happening in a quantum circuit, at least for a single qubit gates. And I posted that. So if you click on 24, that's the slide that we wrote last week. I said, we're going to define the gates through axioms. We're going to talk about the white and the black circles. White is basically 0. 1 is the black circle. Occasionally, I kind of erased a lot of things as I was writing it. Occasionally, we're going to bring in the actual notation that we normally use in the Dirac algebra. And so Hadamard gate is actually producing a superposition. And so when you look at this, you say, what is the deal with the black circle? The black circle really is a set of only one element, and therefore we drop the set notation. So it kind of looks as if it is a classical bit. The truth is that it has more power than a classical bit, but when we write that, that's just the classical bit. So when it comes to give me a 0, so to speak, and put it inside the Hadamard gate, what do you get? I get a superposition, which is a state in which I don't know what's going on, but I know that if I were to measure, I get equal likelihood to get white or black. The same thing is true of h of 0 and 1, and that's introducing the notion of a phase, which you cannot get in the measurement, but which is there and produces what's called destructive or constructive interference. The last gate that we introduced that we never used at all is the Z gate, which leaves the white circle completely unchanged and then puts a phase on the black circle. I indicated that the rules are, besides these axioms, that if I have some operator A applied to a superposition of states, then this is the same thing as a superposition of the operator applied to each one of the states. And so the first thing that I said, we should do in order to understand that these things are ours, is to try to use them to prove this diagram, which is a much simpler diagram than the one that you have in the cubic touchdown from Thomas Wong. So X is going to produce the transformation from white to black and black to white. H is going to transform white to plus and black to minus, and those are basically the superposition of white and white and phase black, negative black. And then the Z does between plus and minus what X does between 0 and 1. I said here set union of outcomes, and Elmar said I don't understand what you're writing. And then we produced here a derivation that basically describes the blue line over here. The blue line says if I have H of white, I get the plus, which is the definition. And if I want to go from plus to H, that's the thing that happens over here. So this is all we did, right? And I can essentially move to the other one and start working on it. But before I do that, I want to sort of remind you, as I did in the meetings, that we have a syllabus. And in the syllabus, there are 4 resources that you need to pay attention to. And the first one is the booklet that I wrote to guide us through the things. So I took Theories for Quantum, I took that formalism and I applied it to a traditional curriculum. And I put stuff on the what's new for you to look at if you want. And I said, if you were to, we talked about some of this stuff on Friday. So if I were to click, it takes me to this location. I say allow cookies, and if this is, I pay for this to be, everybody can access it. So they don't have to purchase it. So if you look at this is what we proposed in 2022. There was sort of set in 2023, and now it's part of the curriculum guidelines, the first knowledge unit for quantum computation in the CS 2023. I believe that you should look through this because it, well, I have the wrong place here. Yeah. This is just the part where we prove that the thing is in fact, I have the wrong thing. How about this one? Okay, where's my paper? So I'm going to have to update that link. This is the second one where we had, we took the first one to QEDC and then we asked them to answer some questions. And then they voted, then we got the data from them. So QEDC is a very large consortium of industrial members in this industry. And then we statistically looked at what they answered and see if there's any problem with the let's see, I think I know where to find it. Anyway, the simplest way is actually if you go here, and if you go to publications, then I think this is the one. And I click on the PDF, and that's the first paper. So in this paper, as you can see over here, what was the basic idea behind the curriculum, and this is the abstract. And I believe that this is a really good read because it says we need to distinguish between quantum mechanics and quantum information science. And after we do that, we have to describe what the goals were and then how we should deal with our students. And then we split this on several components, and then we came up with a bunch of topics. And then we described a bunch of learning outcomes, and we said this is going to be distributed as a survey to the QEDC. And we'll see what they answer and so on. These are all the components, including some conclusions at the end. All right, and so that's something that we discussed with Elmar in particular last time. So okay, I'm glad I found this, and I posted so you can get a basic idea because I struggled last time, and now I struggled finding this, but I struggled last time finding Scott Aronson argument that from a computer science point of view. These theories are like operating systems. And then we said one of the theories that's very big and powerful and just contradicts quantum mechanics. And so at this point, they haven't been unified. And so then when you say with physics, you can understand everything in the world, you have to communicate them both. Between this and that, everything is explained, but the two of them do not agree deeply. So that's still research, not for us, but for the physicists. So then I also have here something in the what's new that says, will you be able to trace with misty states? Sure, I can, and I'll do it in a second, but what is the problem here? The problem is that as somebody gives you a circuit, which is a very simple circuit, you should be able to start using your knowledge of misty states, as we did so far, to trace what's happening in this system. And this actually shows you, if I were to put the gates one by one, this is telling me after the first X gate, the whole thing is one. Why is it? Because in the beginning I have a 0. And then if I put an H, then you have to start getting used to the notation that is used by everybody, which we represent as minus, and that's basically white, negative, black. Then we have an X, which produces this. And so the question is now, what does this mean? Because I see a minus over here. So what's minus 0 square root of 2 over 2 plus the same thing with 1? That's minus minus. This actually changes the minus that we had and puts a minus on top of it. And so then it puts a phase on it. Then I put an H. The minus minus produces minus 1 because the minus produces the 1 through H. And then if I apply X to it, it's going to be the 1 goes into 0, and then the phase stays. And if I measure, I get a 0. But the phase is there before I measure. That's the kind of stuff that you are supposed to become good at doing. Another thing that you should consider this week is you can always go into the first set of notes. And remember that I did write what we should do every week. And in this case, I am saying that we need to introduce 2 qubit quantum gates. And then we have to start the first case of quantum advantage, which is Bernstein-Vazirani, that requires something like a subroutine, which is called phase kickback. It shows up in other algorithms. But in the process, we have to ask ourselves, what are the gates? The gates are axioms, the way we provide them, but also they are matrices. So do you know matrices? And the answer is, of course, but what if I don't? Then in that case, you should start discussing them. So I have linear algebra chapter from Martin Forrest. So back into what I was telling you, what you have 4 different things that you should consider. One is our basically plan of things to talk about, is the qubit set. Then you have the book that I gave you. Most people have a hard copy of it. You click, and that's the website. And if you don't have the book with you or at all, then you can click, take it from here. Finally, you should consider this math primer, and this is taking you to the Waterloo website. And if you click here, you get to download the entire document. What are we working on this week? The probabilities that we discussed last week are not in this document. They are taken from Jim Ferrick's, from edX Quantum Mechanics for Everyone. And that's just physics, and we don't do physics. We are doing quantum computation that uses physics concepts, which we really want to discuss and understand. As we wrote in that paper that I kind of confused with the other paper from Finland, the paper presented in Toronto says, we think that whether they do hardware or not, students are supposed to have an appreciation of quantum mechanics. So they understand the terms. So they could go into engineering, and if they never go into engineering, at least they understand that quantum mechanics is really at the foundation of the entire world that we have around us. So we have to discuss a little bit of physics, but not much. And the probabilities is from that class in edX, and I showed you some 3D implementations of the Stern-Gerlach experiment. But the book that I'm showing you right now has 3 chapters. The second one being linear algebra. So you're going to say now, where is that? Where's the thing that has all the questions that you would like us to discuss? And it's in the tutorial that I gave you last week. Not a tutorial. So it's a quiz. It's called the highlight quiz. And the highlight quiz, I guess it's available. I'll show it to you, right? thq.pdf. That's the thing that you saw that has probabilities as the second section. And then the third section is for this week. Can we warm up to the idea of these notation, of this notation? So can you add 2 vectors? Can you add 2 matrices? Can you multiply? Oh, we have Carla logging in. And I'm just going to write this down now. turns out that we have 7 participants, so is there somebody who I have not included? 2, 4, 6, 7, no, I have everybody, that's great. All right, so now I'm gonna come and say, these are the things that I would like you to start thinking about this week. And then look at multiplication of 2 matrices. Now, we talked about Helgoland. I'll show you Amazon.
Yeah, just Google.
Yeah, absolutely. But the book is just short and incredible. It's just interesting. So this is written by Carlo
So
Rovelli.
you said that in on Helgoland that
He went there.
Heisenberg figured out
Exactly.
the maths that there are only these 3
Matrices, like we have to introduce the gates, and the gates are going to be matrices. If I have the X gate, that's a 2 by 2 matrix. Hadamard gate, 2 by 2 matrix. What about the CNOT? That's a 2 qubit gate, so it's a 4 by 4. So slowly we will have to visit the Bird and the Sutor books. So you will end up with it, but Tommy Wong has the same thing, is that's the math. So you say, well, besides all the matrix thing, are we supposed to do tensors? The answer is yes, and that's the Kronecker product. It's a little bit easy, but unusual. If you didn't have a reason in school to study it and you've studied linear algebra, then you don't know, and somebody has to show it. But it's easy, except it doesn't come up naturally everywhere. But in quantum mechanics, it does. So in this one, you can just read it because it's just an excellent book. It's not math. When you look at the sample, it's just like a story. Yeah, but it's about science, true.
really used to the story understand.
You understand how hard it was for them to come up with this, and that they didn't have any interest in matrices until they realized they have to have matrices. They went back on land and started asking the mathematicians. We said, of course, we have matrices. So then that's the. See?
Linus Pauling was as well there, the Danish guy.
I don't know if Pauli was there. Pauli is fundamental. The three matrices that we were talking about because of him. Okay, so Helgoland is just a really good read, but that's the kind of read that you have. It's no math. It's just somebody struggling and then explaining how struggles. Rovelli knows everything, but he doesn't want to do any math. So we have to understand what these things are, and slowly we're going to worry about imaginary numbers and complex numbers and so on. In fact, that's going to come next. Right, so if this is something that you understand when you go into the math primer, so qubit that we wrote, the Q's for quantum, this primer for young students, see, for the young students. And I want to clarify this. All the questions that I'm asking in the highlights quiz have answers in this document. So all you have to do is to be able to understand what I'm asking and find that location and then see if their explanation is clear to you. And if you still have trouble, then ask me and I will go and solve the problems for you one by one. And the last thing that I want to say is that you need a textbook that is traditional, conventional, and this is the book and everybody knows about it. The idea behind this, and I kind of went through this in the meetings and I'm actually going to still do it, is that he says we should learn classical computing first. That comes in.
So this is the 2022 book or a 2024 book?
The fourth printing, most recent one. You go to his website.
2024.
Yeah. So I show this that this shouldn't be hard for anybody who has done some computer science, but all the gates that you can see over here are very simple and for babies. And these are classical computations. So the question is, what's happening when I'm going to deal with gates which are like quantum? I don't have a booklet for that, but that's what we have studied so far. And so the goal for the book that Tommy Wong put together, which again, I'm going to go to it like this in syllabus, and I'm going to click on this, and you can tell it's a fourth printing. And so the time is 2022, yeah. If you scroll through this, yeah, you will find a table of contents that says, I'm a physicist, and I'm going to teach this to people who are maybe physicists. But what I would like to teach them is quantum computing. So if they don't know much about computing, they have to start with the classical gates and then slowly graduate to the gates that implement the quantum mechanics. And in the process, we stay within the circuit model of quantum computation. Then, as I said, that book is very good because it has a lot of exercises. And his point is that this is for, I'm not sure why I got to lose. How do I get rid of this? Okay. So this is for people who are smart but ignorant. And in the process, using how smart they are, they will become not ignorant because they will learn all of this. So lots of exercises, all the exercise answers at the end of the book. But these are your guides. These are the things that you have to start following. As I said today, if you click on 24, I have what we did last time, which could be, I'm not sure why I'm not taking you the right thing, but so that link is broken. I'm very sorry, but if I don't open image in new tab, now it's not broken. Control Alt Shift H. So you can get big pictures, except I'm not sure why the link isn't good. Friday, June 21 PNG, and where am I sending you here? Friday, June. I think this part here is supposed to disappear. So I will fix the link later. All right, today we are connecting with past and try to introduce a few more things. Let's click on 25. Tomorrow we are going to introduce a diagnostic quiz from CS151 from Berkeley. And that's the quantum computation course that Vazirani is teaching, the 100 level class. I have a link to his form. So nobody says you need this, otherwise you're not going to function. But if a course that is very well regarded internationally, for beginners, 100 level course at Berkeley, which is clearly harder than 100 level courses at other places. If this one has this diagnostic quiz, the question is why? And the answer is, if you do well, then you will be able, if you do well on this quiz, you will function in their class. They don't have any misty states or anything. Everything is super conventional in that course. And the course was offered last time, I think, in 2020 in edX. So you have questions such as these, okay? And all the questions are multiple choice. Our goal will be to understand the questions and provide answers. And probably that's going to be one of the deliverables for this week. All right, now it's time for me to go to Google Colab. And then we're going to do misty states. So Google Colab takes me to this place, and I'm not sure exactly what I have over here, but I'm going to start with a new Google Colab. What is new? No, new notebook. Again, I don't know what I had before, but let me take you to summer of 2022. To give you an idea as to what kind of stuff we're going to do this week in Google Colab. So I'm going to go to 21. And sadly, I have to authenticate. But I promise to make this available to you without authentication. Okay, Shift Tab. And you might say, what are you doing right now? And I'm going to say, I'm showing you how we're going to build a deliverable for this week. What deliverable did we have last week? 2 probabilities problem, each one solved 2 different ways, and a simple circuit. So this year we're gonna this week we're gonna have a slightly more complex circuit that actually implements an algorithm, which is our first case of quantum advantage. And then there will be additional stuff that has to do with the diagnostic quiz that they use in Berkeley. And then all the things that I said you should look through that math for quantum mechanics for the school for young students at University of Waterloo. So the steps that I'm going to provide are kind of like this. I'm going to say, type this. And I'll honestly give you this and you can copy and paste. And I'm going to say, I'm not going to, okay, come on. I'm not going to like this beginning, and I'm going to get a text version of it, and I'm going to paste what he gave me. And guess what? That's my first question. And you remember that this gives you the ability of typesetting mathematics. And so this is the first problem, which I think was already in the, yeah, I lost the thing with Google form. I will have to go to it just to show you. I'm going to go over here, click here, go under 25, click on the diagnostic quiz, and it wasn't this the first question? The answer is yes. Do you need all these answers? What do you need? You need a question and then to answer the question. So that's the first question, and it looks exactly like what they are asking. What's the second question? Is it easy or hard to ask the question the way they want? And I say, sure, why don't you add a second text and copy this? So I'm going to guide you through. You say, wait, I like the fact that I can write math like that, but do I have to come up with everything? And the answer is going to be no. Purpose is so you see how I did these things, and it would be a fairly wide range of equations and formulas. And then slowly believe that you too can research whatever you might need and create beautiful math in Colab if you have to. So I'm going to come back over here and remember that I don't want the code, I want the text. And now this is what I have. Look, what is the complex conjugate of e to the pi I over 3? You say, wait, I don't know how you did that. So if I double click, this is the part that is much more complex. Okay, remember fractions from last time, and then the caret is going to be the exponentiation. Okay, so that's the second problem, which by the way shows up over here, and then you're going to say, I want to see you do matrices. And I say, sure enough. Now I say, how about put all of this in one cell? Okay, I will do it. Copy and come back over here. Notice how it automatically gives me a code cell, but I don't want a code cell for now. And I paste everything in here, and then I say that's enough. So look what I did. I said problem 4. Determine which pairs of matrices below commute. Commute means that if I have two matrices A and B, the multiplication between A and B is the same as multiplication between B and A. All right, so what are those A and B? This is A, this is B. This is A, this is B, this is A, this is B, this is A, this is B. And so there you go, we have matrices. And in the process, maybe you say, well, can you show me how you did one of these in slow motion? I'm going to click here. Double click is the same thing. And so this is how it looks. You start with a begin P matrix, and then you say 1, 1, 1, negative 1. And you have the angle, the ampersand to actually keep things in columns, and the slash, slash, backslash, backslash to actually say that's enough. This is one row, move on to the next row. All these matrices, as you can tell, are basically 2 by 2. So I'm gonna, okay, that's not good. So I'm gonna hit enter, and I'm gonna say, what else do I have? There's another matrix over here. Here's problem 7. Let me do problem 7, and then I'm gonna solve. So I will provide you with this, and you will type it in. Yes, I'll provide you with the answers too. And then you should look at the answers and tell me again if it's possible for you to understand quickly what's going on, or if you need any additional support, help, references, whatnot. So I got this one, and just an example. I'm going to say I don't need this guy, and I'm going to ask for a text entry, and I put this in. And on the right, you can see this automatically. This, but that's all right, because once I hit enter, it looks good. So what's the inner product between the vectors square root of 3 over 2 and 1 over 2? And the other one. So this is basically described in Martina Forek. And that's basically it. So you have the diagnostic quiz. I have some, maybe, do you think there might be some complicated questions? I guess, for example, this question says, could you find a unit vector that makes a certain angle with both the x and the y axis? And then what's the angle between them? Eigenvalues and eigenvectors. Very simple definition, maybe slightly harder intuition. All the books that we have bring this up. You could easily calculate them without understanding them using Wolfram alpha. You just say eigenvalues of the matrix 0, 1, 1, 0. So I'm saying that in this class, what we want is to introduce concepts and hopefully know what they are. Know where to ask for a solution. And then eventually, that's the highest level, know how to calculate the solution yourself. So I go to Wolfram alpha, and I'm going to click here, and I'm going to say eigenvalues of, let's say 1, 2, 3, 4, and I have hit enter, and this says, hey, probably this is a matrix. See, this is a matrix, good enough. And the diagnostic was 0, 1, 1, 0. So I'm going to come back here and say the matrix that I want to deal with is 0, 1, 1, 0. And now what I want is the eigenvalues of this. At least if you get the answer, then you know what you need to check. If you then try to learn how to do it, and you get something, you can say, oh, they say it's -1 and 1. Okay, good to know. By the way, if I were to take the quiz, would I be able to answer? So -1 and 1, that would be the right answer for this question, even if you had no idea what they are. So I'm done with the diagnostic quiz, and the fact that Wolfram Alpha is really useful, seriously useful, and that I'm going to provide everything for you. I did some collab over here, and I'm done with collab right now. So what I'm going to do right now is I'm going to say, if anybody at this point has any questions, please let me know. Otherwise, I'm going to stop sharing. Am I sharing or not sharing? Yeah, let me ask. You are screen sharing. So Sanmeet, has it been working so far? You've seen my screen, or was I just talking without?
Yes, Professor, we saw the screen.
Thank you so much. I'm sorry, really frequently. In 2021, I used to wake up during the night and say, oh boy, am I sharing or not? But now I'm not that panicked. But honestly, genuinely, I would wake up and say, maybe I'm not sharing the screen right now. Crazy. So the chat, are these in our notebooks in Collab? Are these in our notebooks in Collab? So this is a notebook which I just created, and it's in the video for today. I will create this and give it to you so you can create a notebook. So you could say, now I understand how you did it. So
But where do we find it?
that's the thing. Right now, you don't find them anywhere. So if you say, I'd like to find them right now, okay, then in that case, I'll tell you where they are. But I don't know exactly that everybody can get in there because they are under password protection. And if I go into Quantum, so I'm telling you what we are going to do this week. I'll show you where they are, but I don't think that they are ready for you to take them and start working. I hope to. I can send a link. Sure, absolutely. I can do this now, and then you can say I don't know how to access, or I can't, or I can. So if I go under Summer 22, if you click here, then this is this one. That's what I used today. It's the first section 22. Then these are the answers, or some of the answers. So what I wanted to do is I didn't provide anything yet. I'm telling you that they are there. I have to reorganize them a little bit. So for example, when it comes to the first exercise, let me show you the answer that I will provide. I want to go through these and put them together and show you. If I were to come here and say, I will send a link on in the chat in a second, but let me show you what I have. This is lecture 3 from summer 2022. So I say plus text, and I put this in, and when I hit enter, this is the answer. So in principle, let's say that you say challenge us as much as you want. Okay, then I would ask you the questions, and I would ask you to write down the answers in Colab, which I won't do, but that would be a nice challenge. This is what you are supposed to do. The question would say, what is the magnitude of 2 minus square root of 2i? And then the argument is a complex number a plus bi has a modulus which is square root of a squared plus b squared. Then in our case, a is 2 and b is negative square root of 2. So if I were to calculate using this formula, then I would get a square root of 6. I lost again the diagnostic quiz. But if I were to go into 24, so what I'm showing you right now is true, but I'm not yet ready to release this to you, which I will do tomorrow for the week. And if I click on 25 and click here, that's the first question. C square root of 6 is the right answer. And so what I'm telling you is the diagnostic quiz is available. If you want, you can take it. It's not mine, it's theirs, in the Berkeley people. What I would like you to be able to do at the end of this week is understand the questions and also be able to provide the answers, even if you had to resort from time to time to Wolfram Alpha, for example. So, then Carla was saying, where is the thing? Show me the thing. I'm going to say that the link for those people in this room, right, in the online or in this room, I say, let's go to 23. I don't know that this lecture is available to everybody. Some people may be able to get in because I added you to the access list, and some people don't have an IUB network ID, and those people are not going to be able to get in. So if I go into the chat, this is the link to the things that you see on the screen right now. So the thing on the left, I already showed you how to do this one. I could take this one and show you some more, for example. Let's see the answer to the third question. Which one is more interesting? I'm not entirely sure. So I'll take the second question. So the link that you see here in the chat, which by the way, if you're online, you don't see anything, but you see it in your chat, is basically taking you to this document. So if I were to come over here and say, don't give me a code yet, let me type some more text. Then in the text, I paste what I gave you, and when I hit enter, that's question 2 with an argument as to how you do it. What's the complex conjugate of e to the pi I over 3? So it explains slowly, this is what you do. Good enough. If you were to go back now to what I was telling you, the diagnostic quiz, which again, let's give me the thing, but I don't want this one. Then the second question on the 25, you click here, that's the diagnostic quiz. Then the second question would be one of these. So what's the answer that I say? The answer is 1 over 2 plus I squared of 3 over 2. So 1 over 2 plus square root of 3 over 2 times I. So that's the right answer for this question. Okay. So again, all the questions in this diagnostic quiz are relevant because Berkeley does not let people in without. They let everybody in. However, they tell you you're going to have a very hard time if you score 0, for example. If you score up to 3 or 5, but if you score 8, you're going to be okay. If you score 10 out of 10, that's even better. Whatever the number is. So they give you a diagnostic. And they tell you you're going to struggle, you're not going to struggle, you're going to be so and so, or it's going to be easy for you, hopefully. But this is important, okay? And then at the same time, this is not my quiz, but if you want to answer the questions, you can. And if you say, where can I learn how to answer the questions? Martin Lafore, the Math for Quantum Mechanics for Young Students. Okay, so I'm done with the diagnostic quiz. And again, whether the link for you works or not, I will teach you tomorrow how to create a notebook that has all the questions and then all the answers like that. And then the question will be, now that I gave you the questions and the answers, do you understand the answers? What do you need to understand the answers throughout? I mean, just for the sake of knowing that. I'm going to stop sharing and I'm going to go here and say I'd like to share the page screen. Start broadcast. Now I have to go back to my missing state. Okay, so I'm getting, I think there's I need this guy. Do you see it or not? Hopefully. Come on, there you go. So that's the thing that we did when last time. So what I can do is I can move up. That should move as well. Or I can say, I already posted this. And Shivam showed me last time how to access this. So I could just say eraser. There's the big eraser. And then just for the fun of it, I'm going to erase everything right now. And ask myself, what do I need? What else do I need? I want to keep this diagram because I want to finish it. I'm also going to keep what you see over there. The H that appears. Am I in the right place? Do I use the right thing? So is this working? Yeah, but why is it not the right? I don't want that. You showed me how to do the undo. That's right. Double tap. I don't want to enter any text in it. Eraser, where are you? Any erasers or what? So. Okay, I'm gonna write. I don't want to write again. It makes, I don't want to do that, but I don't know how to stop it. So now, all right, let me write. Apparently last time I was able to write with a thick pencil, but now I can't. Fine, so what do we have? We have proved the blue line, you can see the line, right? And we have proved the red line, so I hope you understand that when I say here, H applied to, I don't want that. I understand what mistake I made. I'm writing with a pen that automatically calls for, yeah, come on. I want to select all, but you don't let me. Done. Just leave me alone, I want. Okay, I'm gonna go with this, no, blue, I had blue from last time, okay, that's blue, finally, I got the right thing. So to prove to you that I have the right thing, I'm going to say, I'm going to apply H to, black. And we have an axiom that says that this will produce white and then black with a phase on top. I think it was clearly said by Terry in his video, we do not know why the phase shows up, but nobody knows. And the reason really is because you would like this H to go back to black when you apply it to this superposition. And it's just exactly what I would like to prove right now. So my theory right now is that to prove so I just proved this one here. From black to plus, by the way, I'm sorry, to minus. This is also known as minus. I can just apply the axiom. I'm gonna tell you that the matrices, the gates that we are using are basically 2x2 matrices. And when we provide the axioms, this will become a little bit clearer later when I'm going to actually show you the matrices. But when we provide the axioms, we just describe the columns of the matrix without realizing that is the columns that we're talking about. So I'm going to say I'd like to apply this to minus. Maybe it looks complicated or not, but what I really want to do is to say H applied to this guy. Okay, you know that this is the same thing as saying H applied to H of black. Okay, in some order, maybe the order of the second and the third should have been reversed. But I'm going to say that this guy is going to say, I have to apply the rule that I described last time, that if I have an operator applied to a superposition, I have to use the superposition of the operator applied to every single state. So I'm going to say, here's the answer. And now H is going to be applied to white. And then H is going to be applied to black with a phase. Okay, so hopefully this rule can be taught to anybody that they basically dependent, that H of the superposition of H for every operator, including H of course. And so I'm going to say, what else did you tell us last time? I said that if I have a curly brace, and then I want to put H of white, then I am going to put it like this. H of white, again, axiom is this. And you know, it's a superposition of two states that are equally likely to be produced if you were to measure them. The second one, though, is going to be H of phase. And now you are faced with the following rule that you know, but nobody told you explicitly. If I want to apply H to a phase applied to a state, that's the same thing as saying I'm going to consider the phase operator doing what the operator H was doing earlier. So if this comes out and it's going to be a phase applied to H of black. So H applied to phase of black is equal to phase applied to H of black. Again, it's the same thing with the operator applied to a set of states, in this case just one. It's the same thing as the superposition of the states, in this case just one, H of whatever it is, with a phase on top.
I have a question to the superposition related because
fine. So Elma has a question about superposition. Let me finish this and then I'm gonna answer the question. So I'm gonna tell you, as we discussed earlier, that if I have something like this, I have A or B, but I'm not sure which one, and then I have C, D, and E. These are two superpositions. Then what this means is that the set of outcomes A and B and the set of outcomes C, D, E are supposed to be joined in a set union. So this is really equal to A, B, C, D, and E. So that means that when I calculate here, I'm going to say this is this possibility, and then this is this possibility. But I don't put the curly braces because, as I said before, now I'm taking the set union of these things, followed by something like this. You see, this thing that I just wrote is h of black. And so I have the phase of h of black. That means I have to put a phase on top of all of this. I have to do these things carefully, and I believe that they are very simple, but if I don't practice, I won't be able to do anything. So simple as they are, you need to practice, otherwise you're not going to be able to get the things done. They are not hard. I mean, you can practice calculus, and in the beginning, some calculus requires a lot of practice, and maybe it's not still very intuitive. Hopefully this you find intuitive, but you really have to practice. And perhaps I need to produce a summary of the rules every so often so that we don't forget them. So now what I'm going to do is this. I did already eliminate the curly braces when I talked about the first superposition of white and black. See, but this one here, this one that comes next, is still together as a superposition because it has a big phase on top of it. Now here's the deal. If you have a superposition, say for example, A, B, and you put a phase on it, this is the same thing as, and I told you before, if you have an operator over the superposition, exactly, you put a minus on every outcome, you say, I don't know what outcome is going to come out because it's going to be based on probabilities, but each one will come with a minus because that's what you meant. So it's going to be A with a phase and B with a phase, which means that I'm going to say this guy is white with a phase, and then black with a phase that has a phase on top. All right, now what you're going to do is you're going to say, so that gives me a white and a black. And now I'm going to drop the curly braces for this guy, and I'm going to put a white with a phase, because that's what I have. And then clearly two minuses cancel each other. Minus minus 5 is 5. So this is going to become black. That means that this guy and this guy are going to cancel each other. That's destructive interference. And you're going to get black and black. So, you know, that's what it is. If you read this, it says, I have two outcomes. They're both black. So what's the chance of getting a white? 0. What's the chance of getting a black? 1. So this is, in fact, just black, which is, in fact, the way we write it, just black. But look where we started and look where we are. We say h of minus, which is this, which is this, which starts being this, becomes this. So what I have proved is this part. So now I'm going to say, here's my eraser, I guess. I'm erasing this part because it's done on Friday, but at the same time, what I've done now is slightly more complex, but it's in the same style. It's in the same style. And I guess I'm going to erase this too. I have it in the video because I'm being recorded right now. And if you want, I can, in fact, reproduce it again and create a slide and post it for you. So I'm going to use the eraser to get rid of this, and now I'm going to use blue to say, no, this guy, I guess, right? I don't know, maybe this, yeah. So blue people, is this one. Okay, the blues and the red have been proved. Now we have to do the Z. So I'm going to make this smaller, and I'm going to say, which one should I prove first? So remember the rules for Z. Z says, if you give me a white, I don't do anything to it. And if you give me a black, I'm going to change the face on it. So now I'm going to ask, I don't know, Ashish, which one of the two sides should I go, left or right? Should I go left or should I go right?
You can go left.
Left means that he wants us to go and do this one first, yeah? Okay, so it would be easier the other way around, I have no problem. I mean, because if I say, give me that. No, slightly easier, it's not much. Okay, fine, then what am I supposed to do? Well, I don't know, Z is an operator, so it's applied on a superposition of the Z applied to all those states. That's going to be this. Do a Z on white, and then do a Z on black with face. clearly the Z with white is finished. So you put immediately a white and you say, thank you. Now you have a different story here. You have to take the minus out. So you do Z of black with a phase on top. So then the first step that you did was you say Z of negative something is negative Z of something. All right, that's the linearity of the phase. Just like the linearity of all the operators, where we were saying operator of superposition, superposition of operators. And then I'm going to say here, what do you think happens? I mean, what should I do next? Well, Z of black is going to be black with a phase. Okay, and so that's what Z of black is. But there's a phase on top of this, so I'm going to put two of them. Because essentially this produces white with a black, because the minus minus disappeared. So what do I have? I have just proved that what Ashish was asking me. This guy is in fact minus, and this guy is equal to plus. These are other notations that everybody uses, so we should use them too. I just proved that Z applied to minus is equal to plus. So I proved the arrow. Are you happy, Ashish? Acceptable? I mean, sometimes I make mistakes. If I make mistakes and you catch them, fine. If I don't make a mistake, but you think I made a mistake, you should say so. Because as I said in this class, if you say something good, it's to your credit. But if you say something wrong, it's not your fault. It's everybody else's fault. So let's prove the other one. The other one says, if I start with plus, which is just the conventional notation of Z of white and black. Okay, then what does that mean? Okay, well, let me write it. I don't like how I wrote it. I'm going to say is this. You start with plus, which is basically equal superposition of white and black. Good. Then you're going to say, now I want a superposition of Z of white and Z of black. That's how it is. And so in this case, I'm going to say, what does the first one do? Well, the first one is going to give me a white, and the second one is going to be black with the phase. Oh, but that's minus. Because that's what we decided. So if I use my eraser that Shivam taught me how to use, you are going to say that now with red, I've done this too. No. Boom, boom, so to speak. And, this part is also done. So I finally am finished with this diagram. And these are the transformations for it. Let me say that now I would like you to zoom, can I? I'm going to stop sharing and zoom over here. And I'm going to start sharing here. So I'm going to go back into a Kubica, wherever that is, C290 quantum. That's the class. I'm going to syllabus and choose this guy. And now let's quickly look into what I posted, so that we know what reading assignment you have. So stay, but not in this, put on the list. I can't, I see. So then, because this is not my computer, I have to go into this PC and then C and then users. Common users. And then German and then desktop. Now I can save. And then I minimize this guy, and it's right here, so I can open it now. And I make this big, and I'm sharing so you guys can see it. So what you need to do right now is to take this and start looking at it and see if what I have done is in fact what is written here. There's some forward in the beginning and say, what is this? This is basically 0, but what if I put it in a curly braces, then it's an outcome. Don't forget that it has other syntax is associated with it. And same thing about black and curly brace black. And then here I looked at plus, which I didn't tell you is plus, but it's just a state of two possible outcomes, and they do look like they are equally likely. I say over here that you can prove that it is equally likely, and I say good to know, but let's not get into it right now. And if you just wanted some metaphor, I suppose black and white would be one side of a coin or the other. These are the euro coins, so one side is always different because it's about the country, the other one is common. So the tail for me is common side. And the heads is always different from country to country. this is roughly what a superposition would be. I have no idea what it is, but when it stops, it would be either one side or the other. So I ask you, what is this? And you say, well, this is a set of a superposition. It's a superposition. So how many qubits are we talking here? So let me just quickly check, see if this makes any sense. I don't know, how many qubits do we have in here?
I think only one.
Exactly, it's only one qubit. Why do we have three little things? Because these are the outcomes. If I were to measure that qubit, I would get either black or white. That with what probability? And so Terry says, let's put a white and two blacks to indicate that the blacks are more likely in this case. Then he also says, wouldn't you want to know what the probability actually is? So he has a formula which we go with here. It's in page 83 in the book. Yes.
I have to question this formula because when I see this, right, one white, two blacks, my intuition says it's 1/3 to 2/3. But when I go to the formula, it's 1/5 to 4/5.
Yeah, so-
I don't feel
I agree with you.
this.
There is no intuition here. So if you were to say, look at this guy, your intuition is based on nothing. Seriously, I'm not saying anything bad about you. Like we had somebody saying, I don't know who, maybe Shivam, saying there should be a minus on the white. Two people asked me that. Yeah, well, why? For symmetry. Whose symmetry? I mean, that's not a symmetry that exists in
Yes.
here.
But at least explain me the formula why he have to take the square.
But-
Is it
Very
because
good.
two faces? Is it because we have, or not faces? Is it because we have head and tail? That's why we have the power of two. And if we would have head and tail, and really we would have the power of three.
Yeah, so the answer is simple. This here is an actual qubit notation. You see that it's a combination, linear combination of 0 and 1. That part you understand. It's a linear combination.
Yeah.
What are the coefficients? Some numbers. Square root of 1/5 and square root of 4/5.
Oh,
Now, here's the thing. In quantum mechanics,
So the-
probability amplitude is like energy, so to speak. And so to get the probability, you multiply, you square the probability amplitude. It's not a very intuitive
it's like
rule.
Pythagoras, right? What do you do?
It doesn't have anything to do with Pythagoras, I think. But the idea is that if I have alpha 0 plus beta 1, then the probability of getting 0 or 1 has to do with alpha squared and beta squared. Those are not the probabilities. I agree with you that it's in the beginning, and I made that mistake too. In the beginning, you can do whatever you want with this, and the first thought is the probability should be 2 to 1, right? It's not. I mean, if you want to define it like that, you're kind of stuck. You do your own quantum mechanics and you're not going to be able to get anything going. So that's why he had to go to that particular island, because things were not the way they thought they were. And so he went there and says, what rules do we have to use to make sure that this matches the experiment? So the answer isn't, it looks good, 2 to 1, right? But it's not. So the formula for that is this, because of probabilities that calculated with this formula, that's the formula, I'm sorry, that's the formula, are basically the squares of these things. So one of them has a probability of 1/5, the other one is 4/5. Then the qubit itself will be written as the square root of those probabilities. So unfortunately, this is not and cannot be as easy as this. You can still tell that black is more likely than white, right? But by how much? You need to calculate. And I say, you know what, let's do that later. For the reason is that this is not intuitive. So this is in page 83. This formula.
And
And this is the formula. This is the way you do it. This is the way you, that's the end of it. So that's important. We need to come back to this. Notice that he, other than page 83, he does, which is in the second part, he does not bring numbers up. He says a sixth grader could do this if they only got a so 83 should be on the right. So if they only got a qualitative sense as to which one is more powerful than the other, they're more likely, more shows up more. All right, so that's a very important thing that we need to revisit, because this part is not intuitive in our sense. You need to practice this notation. For example, can you simplify this? And here, look, it doesn't matter what the probabilities are. I can reorganize them and I can see that white, black, black shows up twice. Then I can group them and I say this is white, black, black twice. So then the thing that you started from can be reduced to white, black, black. And then you can actually do it in two different ways. You could then count how many times you have whites and then how many times you have black, calculate the probability, turn it into a qubit, come back and say I could simplify by a number of things. I also say here that if you have NM and then later on you have KM, you can simplify that way too. So as I scroll through this, I warn you about it and I move on. So now the question is, do you understand phase? I suppose you do. You say phase on a qubit is like a minus. Minus minus cancels itself, right? The minus or the phase applied to a superposition, I think you guys found that very intuitive. I have to take the phase and put it on every single outcome. So then if I say minus white and black, that produces the superposition of minus white and minus black. Now we have to go to multiple qubits. I need to go back to my board. Let me see where I want to go. Okay, I'm going to write some experiments before I go into my board. I'm going to go over here, click here, and look at the notebook. So in the notebook that I have here, all right, I'm going to take some of the things that I did before. From my notebook, I'm going to say that every time I want to write I'm really going to start with super simple circuits. My first circuit will have almost nothing. But even that could be confusing because of the ordering and so on. So I come back over here and I'm going to say, I will post this because we did it together today. And then I say, it's not what I need you to look at, but I will write that too. This is just because you want to have what I did in class today. And then I will also show you how to do the whole thing. So I'm going to put this in here and say, I would like to install Qiskit. And the part of Qiskit that prints stuff for me in LaTeX so I can see that what I did with Mr. States is the same. And now I'm going to create a circuit which has 2 qubits rather than 1. And I'm going to ask it to show it to me. A 2-qubit system is not a superposition of 2 outcomes. A superposition of 2 outcomes is a set. You get this or this, it's only 1 qubit. A 2-qubit system is basically like a string where you say AB. AB is not BA, right? Just like, for example, if I write my name ADRIAN and I start switching the order of the letters, I get a different name. So I'm going to close this. I'm going to say get out of clear selected output. And now that I have this thing installed, I'm going to scroll down. I'm going to say, let me create a circuit. All right. So in the circuit that I have over here, I don't want to, sorry. No. I don't want to do anything with the cancel. Just want to do my stuff. So I now have quantum circuit. And so what did I tell you that I want to do? I'm going to create a quantum circuit of just 1 qubit first. This is something that you guys have seen before. And because this circuit exists, let me plot it for you. Ashisha, what do you think it will look like at this stage? If I plot it.
It's just a line.
Not even the line. It's just one. But you're right. It's a line. It's the thing that where the input comes. Sorry. What is the value of this though? So there's nothing. It's just the input. Should be 0. Because when we put nothing on the input, it assumes it's 0. You say, well, you prove it to me. I say, sure, let's do this. So I'm going to say copy and then come back over here and put this in here. And I'm going to say, what is this supposed to do? I'm going to calculate the formula for this guy. And I said it should be 0 because I have nothing in it. So I'm going to come back over here and I'm going to say, in this circuit, which is just one qubit coming in, let me say QC, hey, put an X on the 0, by the way, because there's nothing else. So what I have right now is I have, no, I don't mean AC, I meant QC, right? Okay, so fine, yeah, why don't you draw this guy? Of course, there's a gate right now, and what do you think is the answer? Now it's a one. Why is it a one? Because the zero flipped to, okay, good, perfect. So now I'm gonna come back over here and I'm gonna say, why don't I come up with two? Two circuits. Good, now I have a different circuit.
2 lines.
Yes, exactly. And that's all. But now already potential for confusion. Let me explain. What is the state that comes out of this, which is basically the state that comes in? Let's ask Ashish, what is the state of this guy? If I hit enter now, it doesn't print one anymore because it should print 2 qubits. And what are those qubits that it's going to print?
Well, 1 and 0.
1 and 0 are because I say this is the first, this is the second.
Yeah, well, positive bit 1,
Okay, we got something from Ashish. Emma, what do you think is the answer here?
2 zeros.
That's right, it's 2 zeros. Because if you put nothing, you get a 0. That this thing is coming in. If you don't say what you want to put, it comes a 0. So I have 2 zeros. Okay. Now I say thank you, Elmar, but listen, I'm going to confuse you. But that's my purpose, to challenge you until you say I'm not sure. So I'm going to put on 0.
QC.
Thank you. Elmar is on top of things. Elmar's really hard to trick today. So when I draw this, I have the following question for Elmar. What is it gonna print if there is an X on the first, but not X on the second?
Once now and either 1001.
That's correct. Either 10 or 01. And the question is which one? And now you have to make a decision. So I think Elmar would say, I would say 10. Because we as people and mathematicians or whatever in the book, in any book, we read from top to bottom.
Yes, but numbers
Exactly.
really from
That's
from right to left.
But Kitskit does the following. Takes this circuit, rotates it, and then reads left to right. So I have a video with John Waters who explains that. So the answer here should not be 10, but rather 01. But you shouldn't be confused, except you're more than welcome to be confused the first time around, until we understand the rules. So this comes as 01. Why? Because the first thing that is, am I in Zoom right now? I guess I am. Let me show you something. I believe that I can annotate. So I'm just gonna go and annotate stuff over here. So people are going to read this way. As people, we are going to produce 1 and then 0. I'm in Zoom and I'm writing with my mouse. Okay? But Qiskit rotates the circuit this way. And you have nothing, and then you have an X here. And you say, what's in here? 0. So that's what comes out here. And what is here? 0. It comes out as 1. Qiskit reads like this. After rotating 90 degrees clockwise, it reads left to right. So here I already proved that it's 10, but what comes out of this in Qiskit is 01. And I should be able to say that's the same.
But why you make it so complicated? Because when we have our number system, it's as well 0, 10, 100, 1000, and there is as well 0, 1. So it's just like our number system.
It's just like our numbers, only you told me that this is supposed to be 10. And then
No, I
print
didn't-
01.
You implied that I told you that.
But it is supposed to be 10. Do you know why? Because this is a white. And this is a black. And that's blue, by the way.
Yes, but the 0, right, when you take our number system, 0 is on the right side and the 10, 100, 1000, so it's totally natural to do it like this in a number system.
You think so? Do you think that Qiskit is natural?
Yeah,
Why would I put, oh, I see, you're right, because Q1 is the one, if you say Q0 is the least significant one, it
Yes,
has to be at the end.
yes.
I agree with you. If that's the rule that you use, that's absolutely correct.
it's like numbers.
Yeah, but in any book, you will see it from before Qiskit. Before Qiskit existed, I mean, it started like 3, 4, 5 years ago. So before that, I
It
mean,
was still going on.
it was
That was
exactly the
actually-
same. So quantum mechanics exists for 100 years because next year is the International Year of Quantum Information Science and Engineering from 1925, and then they had 20 years of quantum mechanics before that with more mess than after. But they would consistently read from Q0, Q1 if you had a circuit like this.
Because in computer science, like that's how you like get a representative.
True, but here's the point here. If you start with number 351, that's 351. 3 is basically Q2. And it's like the least significant digit is Q0, that comes last. So you're absolutely right. As long as you don't get confused, that's excellent.
For me, this is perfect.
So where do I go? My eraser here is right here. And I can erase and hopefully you understand. And I will also have to point out that the rule that I use now is in fact the one used by John Watrous. And he explains, rotate the circuit, go left to right. So, so then I guess it's 958. A system of 2 qubits. Let me say, stop share, and I'm gonna come back over here, say, okay. Can I share this one screen? And hopefully that's gonna show up over here, start broadcast. On my slide, I would like to write what's happening when I deal with, I don't want to share the video, I'm sharing the screen, so go ahead and take me to this guy. I'm going to use the eraser and erase stuff. I think you should work additional exercises. So I will try to challenge you with a list of exercises over here. But before we get to the exercises, let me just quickly point out, so I go with this and this, that if I have 2 bits, they usually always will not be the same as BA. If I have ABC and I put a phase on them, that's the same thing as -1 to ABC. That's the same thing as A negative BC, and it's the same as AB with a phase. It's the same as AB with C on top. So that is as if this is a multiplication. And then in the process, we will have to start describing for the first time some gates that basically take 2 inputs. And the gate that we're going to describe tomorrow is the control NOT. This is the target. And then this is the control. And now you say this is a 2-qubit gate. So as a matrix, if we were to drop the matrix of it, how many elements should it have? And it should have 4, because it has 2 times 2, which comes from the Kronecker product, which I didn't explain. But you remember that I told you that we will have to introduce in the MISTY states all the possible axioms, and the actual definition of the control NOT is like this. This is the control, and this is the target. And then the control and the target are going to be in the output. So the 4 cases that describe what's happening over here is if we have white, white, they stay white, white. If I have white with black, they also, the white on the control does not change the target. If I have black on the control, then the target is flipped. So control NOT means that the NOT is going to act only when controlled. So the control stays as it is, and the target from white becomes black. Finally, if I have black, black, this gate, I mean, the description of the gate doesn't look very different from the regular classical gates. You're going to put a white over here. And the reason is a 1 on the control will switch the target. A 0 on the control will leave the target untouched. So now we have the axioms for such a gate. And tomorrow we will be able to use this gate with Hadamard gate to create entangled qubits. We'll have to describe them, and then we will have to use them. So I guess I'm done for today. I managed to barely introduce systems of qubits and talk about the phase in that context. I managed to write some more practice exercises, and I introduced the second deliverable for this week, the second week. And I promised that I will produce a deliverable that you can follow and check and understand and ask questions about. And I will also give you some exercises for more practice with MISTY states. And then we will do phase kickback, and also we'll do Garcia-Vatirani, and that will be the week. Now let's see, where is the Zoom? Zoom is right here. I'm going to stop sharing. Any questions before we stop? I'm going to now in the chat we have, it won't let me in. It's okay. I agree with you, Carla, because it has a password. So I'm going to bring it outside of passwords and then I'll share it with you for tomorrow. Let's see, the video is right here. So I'm not sure how many people are still in, but this is the end of our lecture. I'm going to click participants out. So if you have any questions, let me know. Otherwise, at 11, I'm going to start those meetings and we're going to go over stuff together. 10 minutes, 15
One
minutes.
question
Yes.
to the book, because he writes here that about superposition, that then we say the ball is black superposed with white.
Yeah.
Would it be the same when you say it's white superposed with black?
Yeah.
This is invertible.
Yeah.
Yes. Okay. Yes.
So very briefly, the question is what superposition, and the answer is nobody knows really, but people have all sorts of models, and I posted one such model, and if you go over here, the model is kind of like this. So this is a superposition of three things, and if you look at it, what object can go through these by filling them completely, and here's the superposition of the three things. So if you ignore the triangle at the bottom, could you say that the circle is superposed with square, or the square superposed with circle? It doesn't matter. It means that you could get either or.
But when it's a superposition
It is.
of circle, square, and
the triangle, that's
then that's some.
But you don't get those.
Chaotic.
You do not get those until you project on one of the planes.
Yes.
You know, it's very hard.
Yes. Yes,
What
you're
do you have? I have this weird object that looks really strange. I also said that this thing was taken to the extreme, right? I get three people, right? That's the object that produces that, but I have to send the light properly from a certain place, and then I get Gödel, or I get Escher, I get Bach. Right, so that's a more complicated superposition. These are two people who came up, Kuiper and Van Baalen, you know, whatever the name is, I don't know if I say it right. So the superposition is this, which makes no sense. But once you project, so remember that this says we are two-dimensional beings in this example, and somebody gives us a three-dimensional object. We do not know what that means. But if we project in our world, we know that it could be a square or a circle or a triangle. So you say, is it white with black or black with white? Both. Both are fine. The idea being that if I get a ball, it's going to be the black or white. The order doesn't matter. Yeah.
Thank you.
Thank you so much, and I will be in touch. I will go to the meetings, and then tomorrow I'll post exercises and the notebooks for you to start following around. Thank you so much, and I will stop sharing and stop recording, and I'll see you later. I'll stop recording here.